Hi everyone, welcome back to Code Something. So often in computer science we come across differentiations and integrations. Um, like this concept might, like we are used to solve equations and, but we're not really familiar with application real world. So we will just brainstorm or go over the concepts of differentiation, so that we can understand their applications in real world. So when videos will probably referring to this video link, so we can actually come back here and then refresh our memory on differentiations. So often I pick problems from real world so we can understand in a much better context. So let's take an example to understand what differentiation does. So let's see if you have a function, say f of x, and it's varying with time. Let's say this function over time varies something like this. So in this case, we can take differentiation of this function over time, or dx by dt, something like that. Let's say we introduce like one more variable. Let's say this is x, this is y, and let's say over time it's being varying to different properties. So to define a definite value for this function, not only we need to know the position of y, but also we need to know x. In that case, we'll do something called a partial derivative. That is something like you keep y as a constant term and then you take differentiation with x, and then you keep x as a constant term and then you take differentiation with y. You can apply differentiations multiple times. Let's say this is your first, you take differentiation for the first time, that is first order derivative. If you take differentiation again, this is the second order derivative that's going to be represented as d square f of x by dx squared. Let's take an example to understand what we're trying to imply here. Let's say we have a wall and then there's a ladder leaning on the wall. Let's say this ladder is say 15 feet in length, and the tip of the ladder in the bottom is like around say 10 feet from the ground, from the wall. Now let's say there's a person who's pushing this ladder in the negative z-axis direction at a rate of 1/4 feet per second. Now if I ask you a question, let's say after, let's say 12 seconds, what is the rate at which the tip of the ladder is moving in positive y direction? So what we're trying to find here is a change, or at what rate this tip is moving with respect to time. Or if I represent this as x and y, what we're trying to find is dy by dt. Now we can say dy by dt, but we see that there's a differentiation has to be done in, like if you keep x as a constant, then it's dy by dt, but both parameters are changing, so you gotta keep partial derivative in this case. Well, now this is a problem, right? Now how do you solve this question? So we have to use some connection or relation between the terms to achieve this task. So what I'm going to do is I'm going to use Pythagoras theorem to write this equation. Now if I differentiate this with respect to time, I will get 2 into x to the power of 2 minus 1, this dx by dt, plus 2 into y to the power of 2 minus 1 dy by dt in is equal to 0. Now, so what we know is for every second we can move 1/4 feet. So at 12-second time instance, we would have moved by 12 into 1 by 4, that is 3 feet. So at position x, which is basically 10 feet, after 12 seconds we've been moved somewhere here. I'm going to call it as x dash. So at x dash, the length is, we have moved by 3 feet. It has to be 7 feet, 10 minus 3. Or the delta x is 3 feet. Right? Okay. So once we know it's actually 7 feet here, we can use the equation again to compute the new y. That's going to be y squared plus x squared with 7 feet square will be equal to 15 feet square. That is like my new position, something like this. So now we can compute the value of y. That will be equal to square root of 176. So with this equation, if we plug at this instant, let's say time t equals to 12 seconds, my x will be 7, my dx by dt, the rate is still the same. The change happening in y x direction is still the same. It's 1/4 feet per second. So I'm going to do dx, again the dx by dt is change was 1/4 plus 2 into the new y at time instant t equals to 12 seconds. My y is basically, we found out it to be square root of 176. So that into dy by dt. So at that instant, the change happening in y direction with respect to time is going to be equal to 7/4 into 1 square root of 176 feet per second. That's an interesting problem. So quite often we use differentiation to do some other things, like if you were to have an equation something like this, and at any instant of time, or maybe x, let's say this is x and y, and it's a parabolic equation, so it goes something like a into x squared as an example, let's say. So at any instant of location, if you take a differentiation of the point, we're going to get a tangent to the point. That's nothing but the delta y by delta x. That's going to be slope, right? So if you'll take a difference between two consecutive points, since it's going in the downward direction, this y and this y, the difference is going to be negative because this y is less and this y is high. So the difference is going to be negative in this, whereas in this case, the y here and y here, the difference is going to be positive because the y value is more than this point. But so when you take a difference between these 2 points, we're going to get some value for difference. So what we do in differentiation is going to be, we will considering the small difference as possible. So if I were to zoom into this equation, the curve is going to look something like this. We're going to take a difference here, the delta y delta x. For a very small change in x, what is a change in y? So that's the differentiation. If I come to this point, the curve is like almost flat. So for every small value of delta y, the delta y is almost equal to 0. So the slope is almost 0. So we can often, like given an equation, we can say that, let's say if the equation is f of x. So this equation is going to be having the minimum point when f dash of x equals to 0. If we equate the differentiation to equal to 0, we're going to get the minimum point of the equation. It has interesting application. So let's see a real world problem to understand the concept here. Let's say I have a building and I need to put a fence across the building, something like this. So now let's take some real-time values. The length of the fence is x and it has the width of y. Now I need to like arrange my fence in such a way I get the maximum area possible. I need to get the maximum area possible. So how do I do this thing? So we will have two equations here. So we know that the let's say the total feet of length is 50 feet. So we can represent it as 2y plus x equals to 50. That's my condition. And we know the area has to be maximum. That's our condition, right? So the area has to be equal to x into y. So what we're looking for here is basically we try to differentiate this and equate it to 0 so we get the maximum point or extremum point. So using this equation, we can represent y as 50 minus x by 2. 50. So if I do this, then I'll be getting my equation as sorry, I made a mistake. So this is the equation. So we have the area equals to y into x. I want to represent this in the form of y. So that's gonna be my 500. So I'm gonna take say 500 feet. Sorry, I have a problem here in my textbook, so I'm referring to the same textbook. So we have 500y minus 2y squared. That is something like a is equals to y into ax. That is y into x. We will solve this equation. That's going to give us 500 minus 2y. And if we solve this, we will be getting a is equals to 500y minus 2y squared. Alright, so now if I take a differentiation of this with respect to y, that is dA by dy, I'll get 500 into dy by dy, that's 1, minus 2 into the y to the power of 2 minus 1 into dy by dy, and that's gonna be y 500 minus 4y. So the area is maximum. My differentiation, that's the dy by dy, will be very minimum. So that's gonna be the change in area will be very less. So that's gonna give me 0 as equation. So this is the value. So we'll compute the value of y to be equal to 125. So we know that when y equals to 125, we're gonna get maximum area possible. So we will solve the first equation to find the value of x. That's going to give us 250. So for a combination of 250 as x, if this is my fence, I need this to be 250 and my y to be 125. That's the possible arrangement we can get to get the maximum area. So that's an interesting problem to solve, right? So so this is the first order derivative. So what happens in second order derivative? That's an interesting question to look at. So when we have an equation, so if we take a derivative of the equation, that's going to give us the change in the values. So I actually made an equation like a graph. Let's take a look at this. So let's take, for example, there's a x and y coordinate, and this is my image. And in the image, I have like a black band in between. So if I were to take the derivative, like if I were to plot this in a three-dimensional plane, that is my x-axis, then y-axis here. And if I were to plot the value of intensity of each pixel, I would get one more dimension. There's my z dimension. Or I'm going to represent as equation as f of x and y. That's going to be my intensity curve. So it would look something like this. Now, there's not a like a sharp change. It's going to be like a smooth transition. Like it's going to be a little bit of high intensity, and it keeps dropping. It's going to be like a smooth edge involved. So that's going to be a different curve. Now, if I were to take the differentiation of this thing, that's going to be change. We're going to be computing the change in the value. So the change between the pixel values is almost 0 here. The change between the pixel values again is almost 0 here. But there's a constant change involved along this curve. So we will get a differentiation of the first order, something like this. Now, at what rate this change is happening? So the first order derivative was the difference between the pixel, like at what rate the change was happening between the pixel. Now, if I were to plot all this rate and check at what rate the rate is changing. I know it's going to be confusing here. Let me just put some numbers here. Let's say we have the pixel as say 100, 200, 300, 200, 100. So we can see that there's an increment in value and there's a drop in value, right? So if I were to take differences between the pixel, that's going to be 100, and then 100, that's going to be 100, and then 100. So we see there's a constant difference between the pixel. So that's the change we're going to keep plotting here in this domain. Now at what rate this pixel is being changed? That's going to be, if I were to take like a lot number of values here, we can see there's a change going on between these numbers. So if I were to look at this point and this point, the difference is going to be dropping here. Now in second order derivative, what happens is we're looking at what rate the change is happening. We're not measuring at what rate the pixel values are changing. We're checking at what rate the rate is changing. So if I look at this point, the rate at which the pixel values are changing is almost the same. We can look here, right? So what happens at this point is the rate at which the pixel value change is almost the same, so it's going to be dropping to 0 here. Again, if you were to look at any at this point, the change is almost same. The change is almost a constant. So the difference between this constant is going to be 0 again here. But if you look at this curve here, this is interesting here, because what happens here is there's a constant increase in the value. So that corresponds to this point here. And there's a constant, it's almost getting a constant here. There's a drop in the change. There's a drop in the rate. That's going to be dropping here. And if you were to look at this point, there's a constant decrease in the value. So there's a drop in the pixel value, drop in the rate change in pixel values somewhere along this point. And again, it's almost getting constant, which means the change is increasing, and from negative it becomes positive, approaching towards positive, and there's going to be constant 0. So it converges at 0 and then goes like this. This is a new curve we get. It has an interesting application in the Laplacian edge detection algorithm. So we're going to use these equations to find edges in a matrices, so we can make our computation process much more easier. I'll come back to this with much more in detail when I'm coding the OpenCV, so we can understand the actual working of differentiations, like higher order differentiations in actual code, so we can see their applications in real time. All right, thanks for watching.